Okay, so still in section 1 of chapter 21, enolates. Again, I've talked about this in class, so if you got enolates, then good. So enolates are formed when we take a proton off of a carbonyl-containing compound. Okay, so again, I'm using this ketone here. This is the same. You'll recognize this from the enols if you haven't watched the enol video. So the 5 alpha protons shown here, any of these could be deprotonated. And these are going to have pKa's for this ketone, right? The pKa won't be exactly the same for all of them, but pKa is going to be somewhere around 18 to 20. If we have an ester as the carbonyl compound, so if it's an aldehyde, it'd be a little lower, maybe 16. If it was an ester, it'd be a little higher, maybe 22, 23. The point is, protons on alpha carbons are more acidic than most CHs. Okay, so remember the carbonyl is an electron withdrawing group, so it's pulling electron density away from the 2 alpha carbons. That's going to in turn pull electron density away from the protons. It's going to make the CH bond more polarized. And then if you pull that H off, you get what's called an enolate. So I've even left this up from the enol video. So an enol has an OH bonded to a carbon-carbon double bond. All right, and that's a firm structure. An enolate, this is just one of the 2 possible resonance forms, and this is what they mostly look like. Okay, if you take an X-ray crystallography picture of an enolate, the carbon-carbon bond distance is like a carbon-carbon double bond. Both of these atoms are trigonal planar. The CO bond looks like a CO single bond. So they look like this, and hence they're called an enolate, because you've got an O- bonded to a carbon-carbon double bond. Sort of looks like a carboxylate, right? The carboxylic acid analog, let me come over here and mess with this E-enolate. Okay, so the stereochemistry of the enolate there is E. I went through this in the enol. If you're wondering about stereochemistry on enolates, go look at the enol chapter, or video. Here, this kind of looks like carboxylate. Okay, so I guess I should put the double bond over there and then the chain off there. Okay, so that the carbonyl delocalizes this charge, makes this really stable. Carboxylates are quite stable. They're weak bases, but they're a really stable anion. Enolates, on the other hand, are not all that stable. Okay, an enolate is a very strong base and a good nucleophile. I'll talk more about that in a second. And you can also draw a resonance structure here. Where there's negative charge on the alpha carbon. Okay, so if you pull one of these alpha protons off, the carbon it's on becomes essentially negatively charged. So this form of the enolate is not dramatic. It's not a real good representation of the structure of the enolate, but it's an excellent representation of the reactivity of the enolate. Okay, so this is going to be a strong base. All right, so what does that mean if it's a strong base? Well, it means that if there's even a weak acid around, the enolate's going to get protonated. So enolate reactions have to be run dry. Let me phrase this differently. So they're strong bases, so they react with OH groups, right? And OH, an alcohol is a weak acid. If there's a strong base reacting with it, it can do that. They're also good nucleophiles. Enolates are good nucleophiles. So an enolate can do an SN2 reaction. So you could have, just for example, all right, if I make that enolate, I can do an SN2 reaction. Okay, but if I tried to do the same reaction with ethyl iodide instead of methyl iodide. So up here I have the enolate attacking a methyl iodide. Remember, methyl iodide doesn't have any beta protons. It can't do elimination chemistry. So that SN2 pathway is the only one it can do. Now, right, so we can do the SN2, but remember what you know about strong bases in SN2 reactions. If there's a beta hydrogen around, you can do E2. And in fact, the E2 reaction in this case predominates, okay? So you make this really strong base, and it's just going to do E2 chemistry. So look at the malonic acid and acetic acid videos. Okay, so cross-reference. If you're wondering how you do, how you add electrophiles on the alpha carbon that aren't carbonyl compounds, take a look at the malonic acid and acetic acid videos. Okay, so I'm going to take this stuff off now. Remember, unlike real class, unlike class where you're sitting in front of me and your eyes are glazing over and I'm trying to ignore that, you can pause this. So if your mind starts to wander, or if you need to see something again, rewind it and look at it again. If you need a break, get up and walk around. You're not going to offend me. I'll just stand here like so. Okay, so good nucleophile. These also react with other carbonyls. So an enolate will attack a neutral carbonyl compound. And we make a new carbon-carbon bond. All right, now obviously that O is probably going to get protonated. You can also do eliminations. And so look at the aldol video for this. Okay? So enolates are strong bases and good nucleophiles. Let's talk now. So the next thing, let's talk. We're not talking. Even when we're in person and I say that, we're not actually talking, right? You're just writing my stuff down. So the next thing I'm going to show you is how we make an enolate. Okay, so I've shown you, I've described the chemistry of enolates. They're strong bases and good nucleophiles. I've given you 2 videos to go look at and follow up. How do we make them? Well, an enolate is the conjugate base of an enol. Okay, so the conjugate base of an enol, if you're making a conjugate base, you're pulling a proton off, that means you have to react with a base. So to make an enolate, again, I'm going to go back to acetone, but this works for any alpha proton. All right, we need a base. That base pulls this proton off. Remember, the CH bond's polarized by the electron-withdrawing carbonyl. And this gets us the enolate. So I've drawn it to the right. The question is, what about the back reaction? What is the equilibrium constant here? And for any equilibrium constant in an acid-base reaction, it comes down to the pKa's of the acids, the stabilities. Okay, so if we take, let's do acetone and hydroxide. The acid on the left is acetone. pKa is about 18. The acid on the right is water. The pKa is 15.7. Okay, so the weaker acid is favored. That means the left is favored. But by how much? Okay, so the equilibrium constant here is 10 to the 15.7 divided by 10 to the 18. Okay, so boil that down. It's about 2 orders of magnitude So let's call this 0.01. It's a little less than 0.01, but there you go. About 1% of the mixture is going to be here on the left. And that sounds like, well, crap, that's not much. It's 1%. 1% is maybe a bad number to throw around right now. 1% is significant, okay? Think how many people you know. You probably know, your 20-year-old socially active people. You probably know a few thousand people, right? So 1% is, let's say you know 10,000 people. 1% is 100 people. That's a significant number of people. So in solution, remember, we've got like, if you have a mole of this, 1% of a mole is 10 to the 21st. So there's a lot of this. And so we're going to see aldol reactions. The upshot of this is, so we'll see aldols with weak bases. All right, the simple aldol, and I have a video up already on that, an aldol with a weak base. All right, so I'm going to erase this one now and do another one. So here's a base called LDA, lithium diisopropyl amide. I said this in class, a negatively charged nitrogen is called an amide. It's not the amide functional group that we studied in chapter 20, that's nitrogen bonded to a carbonyl. All right, so now, and this is a lithium enolate. Okay, so pKa is 18 again. pKa here is 34. All right, the weaker acid by a lot is diisopropylamine. Right, 16 orders of magnitude, give or take. So now this reaction really can be imagined to be pretty much complete to the right. Okay, so you've got a big difference in pKa's, big difference in stabilities. The enolate's way more stable than this negatively charged nitrogen. And if you want to think about that, you've got a negative charge delocalized over an oxygen, most electronegative element in the mix, and a carbon. So a delocalized negative charge involves some oxygen versus a localized charge on nitrogen. So the right's going to be bigger. So so this is essentially an irreversible reaction to the right. How about some other bases that do this? So irreversible, I'll come over here, making this probably too busy. I'll just stand in front of it. So bases that give you an irreversible enolate formation. LDA, sodium hydride, NaNH2. That's pretty much it. That's what we're going to use in this class. Even sodium hydride and sodium amide, I don't like that much. Really, in this class, the point is to give you reactivity paradigms. There are thousands of bases, okay? I can show you giant textbooks on bases that will make enolates. The one that's most important here, the most critical, is LDA. Okay, so reversible bases that are going to give you reversible enolate formation. So we did one, hydroxide, and therefore, any of these alkoxides, right? Triethylamine and any amine base. Okay, so that's pretty much where we are with reversible bases. So again, what I'm calling an irreversible base, these bases, if you treat a carbonyl compound with an alpha proton, will irreversibly make enolate. The reversible bases, hydroxide, alkoxide, triethylamine, those, if you treat the same compound, you'll get that enolate, but reversibly. You'll have just a small amount of the enolate at equilibrium. Okay, so the next videos are going to discuss chemistry using enolates. I think the next one I'm going to do is an aldol. All right.
probably too